Oh, okay. Let's get started. So, in the previous class, we learned about the recursive function, right? So I hope everyone can understand how this recursive function is working, in RISC-V, right? Also, so I posted the homework number 2, right? And then, so actually, I provide the homework questions in order to make you practice it. Okay, so and then in the homework questions, so you can also find the some function. Okay, so, and then also, and then in this question, then you need to figure out the return address and then some the the target of a branch instructions. Okay, so please try to answer the homework questions by yourself. Okay, this is the good practice. This is good practice for exams. Okay, exam questions. And I believe the the difficulty level of the exam questions is can be similar to the some difficulty level of the homework questions, right? So this is a very good practice for to be prepared for the exam. Okay. So okay. So now so so in this class, I hope we can discuss about the machine code, how the how the assembly instructions are encoded into the machine code. But before to this topic, so I will briefly explain about some miscellaneous topics in RISC-V instructions. Okay, let's learn about the pseudo instructions. So what does pseudo mean? Okay, a pseudo means it means the fake, right? It's not real, right? Okay, so pseudo instructions. So pseudo instructions mean that these instructions are not actual RISC-V instructions, right? So in the beginning of this chapter 2, so I explained that a processor receives instruction and processor generates the output of instructions based on the some promises in the RISC instruction set architecture, right? And then what are pseudo instructions? Pseudo. So pseudo means I mentioned that pseudo means it's a fake, it's not real, it's not actual RISC-V instructions, but in the assembly code we can use these pseudo instructions. So actually pseudo instructions are defined for your convenience. Okay, so and then we can easily use these pseudo instructions, but it's not actual RISC-V instructions, right? So actually, when a pseudo instruction is executed, this instruction is decoded. So this instructions is also translated into real instruction. Okay, so you can just understand that pseudo instruction is just some definition in C. So in C, we can just define a certain custom function using the define, right? So like this defined function, so you can just understand that pseudo instruction is a kind of defined, not actual instruction, but it's a defined instruction. Okay, so let's see just the example. So I believe you can easily understand the concept of pseudo instruction. So this slide shows the examples of pseudo instructions. So if you see the RISC-V assembly code, so actually in the in the dump file. Okay, so in the left assignment, so we can generate the dump file, right? And then you can observe some RISC-V instructions. But I believe you can find some some instructions which are not defined by ISA. So instruction list in the textbook. So for example, you can find the read. It means return, right? But actually, the meaning of return is the JALR 0 RA 0. So what does that mean? So this is the JALR instruction, and then 0 is the RD, the destination register, and then what is this? This one? So RA. So PC is updated by RA plus 0. So 0 is the offset, and then the next PC is stored in 0, right? But I mentioned that 0 is not updated, right? 0 is just 0, right? So it's nothing, okay? The update is not performed. So, and then, so actual instruction of this return, RET, is JALR 0 RA 0. But in assembly code, we can use this instruction, return, okay? So in the RISC-V assembler, this return RET instruction is decoded into the JALR 0 RA 0. And then actually this instruction is executed in a RISC-V processor. Okay. So these are the examples. J immediate, it represents JAL 0 immediate, right? And then JAL immediate is the JAL RA immediate. Okay. So let's learn about the meaning of label. Okay. So in the code, we can also easily observe the labels. Okay. So labels are targets of branch instructions. So this is the example. So this is the RISC-V assembly code. So it's a JAL, array, and simple. Okay. So this is the jump instruction, and then we know if this instruction is executed, then we can jump to the position of label. So, but you can find that actually. So this is the text, right? It's a text information. So actually, and then we learned that the JAL includes the immediate field. So which means that actually the JAL is the JAL, and then RD is the destination, and immediate. This immediate represent the target. Then, but we can observe that JAL is used to, and then actually a text is used in the JAL. So it means this text is translated into the immediate number. It's a constant number in this case. Then how can we calculate this number? So also you can find the question in the homework number 2. So we already know that JAL jumps to the simple. The target of JAL is simple, and then where is the simple? Simple is here. The label simple is here. So in order to calculate this immediate number, so immediate number is the PC. So this is the program counter of this JAL, and then this is the program counter of the label simple. Okay, so simple represent this PC. Okay, so in order to calculate the immediate, then we can just calculate so this is the PC of the simple, the label simple, and then minus the PC of this JAL. So it's actually 0x because it's a hexadecimal number. So it means the immediate number. So this simple represent the 0x to 1c. Okay. So actually this instruction, this JAL instruction is the JAL RA and 0x to 1c. Okay. Sorry. So when this JAL instruction is executed and then it's given to a RISC-V processor, actually this JAL RA 0x21C is executed. Okay. So you can calculate the this label like this. So also you need to know that immediate. Sorry. So if we use the immediate number in add I or add I or some other instructions such as the load word or load byte, then I mentioned that immediate is the 12-bit 2's complement number, right? So, so when we use the immediate number in jump or branch instructions, then this immediate number must be multiple of 2. So it must be an even number. Okay, so it must be multiple of 2. Okay, we cannot use an odd number in this immediate field of the jump or branch instructions. Okay, so we'll learn why this immediate must be the multiple of 2 later. Okay, this is because this is some encoding or decoding issue. So it's a hardware issue, but so you need to remember that in a jump or branch instructions, this immediate must be multiple of 2. Okay, so we can calculate that is simple, the immediate number like this. So it's a PC of the target minus the PC of the jump instruction or branch instruction. Okay. So, and then sometimes we may require long jump. So it jump to the very different position, very different position of a program. Okay, so for this operation, the RISC-V supports the special instruction like the AUIPC. So, uh, so so you may observe that this instruction in the dump file, right? So it's like the hello.c in the hello.c, and I believe you can observe the AUIPC. So this is used for a long jump. Okay, so long jump means that actually we can use the 20-bit immediate number for JAL or 12-bit immediate number for JALR, right? But the range of this number 12-bit is rather it's a small. Okay, the range can be small, but we may want to jump to some very different position of program, right? So in this case, we can use the AUIPC. So in order to make the large constant number, we can use the LUI. So AUIPC is the LUI version of this jump instruction. Okay. So if we use the AUIPC and then immediate number, then it just update. So it just update the RD using the current PC, the PC of this AUIPC plus the immediate number. But this is the 12-bit immediate number, but it occupies the upper 20-bit of the 32-bit field. Okay, and then the lower 12 bit is filled with the 0. So it's similar to the LUI, but the meaning is a little bit different. Like the RD is the PC plus period number. So then how can you fill this lower 12 bit? So we can use the JALR, like the array, and then lower 12 bit. So it's similar to the LI, right? So we can make very large constant number using LUI and add I, right? So like this. So we can also uh, make the large jump point, right? Using the AUIPC and JALR, right? So this is the pseudo instruction, the summary of pseudo instructions. So as I mentioned, you can find these pseudo instructions in the RISC-V code, RISC-V assembly code. Okay, so like the J label means the JAL 0 label. Okay, also you can find the move instruction. So move instruction means that it move the data to a source register to destination register. So you can find the move instruction in the RISC-V assembly code, but actual instruction is add I. Okay, the meaning is the same, right? And then not. So not is the bitwise not instruction. So this inverts the every bit, but this is the exclusive or immediate, and then -1. Why? Actually, A exclusive or 1 is the not A, right? So -1 is the 1, 1, 1, 1, 1, all ones, right? In the 32-bit data. So this is the bitwise not. So exclusive or 1, all ones is the not A. And then nope. So what is nope? Nope represent no operation. Okay, this it represent no operation. So no operation means that it just consumes one clock. Okay, and then it does nothing, no operation, but it consumes only one clock. So this is the actual instruction of nope. Add I 0, 0, 0, right? And then and then we can use the Li to generate the very large constant number. The LUI can be translated into the two instructions, LUI and add-I. Okay, so this is the code. So we just learned, and then also you can find the BGT, and then it means that the branch if greater than, right? But actually, you cannot find this instruction in the RISC-V instruction list. So BGT is actually BLT. But you can find that these registers are, the order of register is changed, okay? So these are pseudo instructions, not actual instructions. But we can find pseudo instructions in the RISC-V assembly code. And then pseudo instructions are actually translated into the actual instruction like this. Okay, so if you observe some pseudo instructions in your dump file, then you can understand, oh, these instructions are can be just translated. Okay, and then let's learn about the arrays. Actually, we already learned about the arrays, right? So what are arrays? An array is group of elements, right? Like, so we can just declare arrays like this, like int a 5. Okay, it means that this is on this declares an array A, and then this array includes 5 elements. And then you can use the data in the array using the index. So this is the index. This is the index. Okay. So this array has the 5 elements, like from A0 to A4. And then in order to identify a certain element in an array, we can use this index number, right? So using the index number, then we can just access the data in the array, okay? Then how can we access the array? So I mentioned that if we declare a variable, this variable is allocated in memory, right? So allocated means that, oh, I just declared the variable A, then the memory space. The memory space is allocated for this variable A. It represent address. Address is also assigned to this variable A, and then using this address, we can access the data of A. So this is the meaning of variable declaration, right? The variable is declared, so it means that we allocate the address, the memory space to this data, right? Then how about the array? So array means that array includes multiple elements, right? So which means that the memory space. Memory space is allocated to these multiple elements, right? And then actually we can calculate the address of other elements like this. So this is the base address. So this is the base address of an array, and then actually the base address represents the address of array 0. This is the first element of an array. So this is the base address. And then using this base address, we can access the other element. How? We can just increase the address of the address of the next element using the size of a single element. So if the size of a single element is 4, then we can know that the address of the next element is the base address plus this 4. Okay. So in C, we can just figure out the size of a variable using the size of, right? Size of int, right? So in order to access the next the other elements in the array, then we can just use this the difference of the two elements as the offset. Okay. So this is the example. So this in this example, the array 5 is declared, and then we can just access the array 0 and array 1, and then array 1 and array 1. So it's simple. And then, so firstly, we need to figure out the base address of one array. So this is the example. So in this example, the base address of array is stored in S0, right? So this is the 32-bit data. Okay, so we are learning about the 32-bit computer system, right? So it means the size of an address field is also 32-bit. So which means, oh, we need to generate the 32-bit constant number. So we can use the LI, but actually LI is the LUI and add I. So the base address is the 0x123b4 b4780. Okay, this is stored in as 0. So then in this example, array 0 is array 1 multiplied by 2. So this is just actually it's not 1. It's typo, it's 0, right? So firstly, we just load the array 0 from memory, right? Using this address. So you can find that offset is 0. Okay, so this is the array 0. Okay, and then in order to access the array 1, you can find that offset is 4. So it is because the size of integer is 4 byte, right? So it means that it can access the array 1. So we can access the element of an array using the base address plus offset in the load instruction. Okay. So this is another example. Okay, another example in the iterative loop. So we can easily observe this type of code. So we can define a large array, okay, and then we can repeatedly apply the same operation to the each element of an array. Okay. So you can find that spot. So in this case, we need to increase this number, this index, right? So actually you can find that. So this the address is increased. Okay. So this address is increased by 4. Okay. 4 is the byte offset. Okay. So you can find that T0 is so you can find the index. Index is increased by 1 because we used I++, but because the size of integer is the 4, which means that the address of this element of this array needs to be multiple of 4. So for this purpose, we use the SLLI. So it left shift by 2, and then it is equivalent to the multiplied by 4. Okay, this is the I multiplied by 4. So using the T0, then we can access each element of array. Okay, so this is the example of array accesses in a iterative loop. Okay, and then this is some very simple topic is ASCII code. The ASCII code represent that it represent characters in using the binary number. Okay. Okay, so array versus pointers. So actually, the array we can easily understand how arrays work and how the arrays are accessed. Okay, so we can just access the element of an array using the array indexes, right? But we can just access the data in array using pointers, right? Pointers in C. So this is the example code. Okay, so in this code, so this is the array version. It's the array version. This is the pointer version. Okay, so you can find that. So in this example, so in the array version, we just define the index of an array, right? And then we just increase the indexes of an array, and then we can access the each element of an array. But in the pointer version, then this function receives the pointer type data. Okay. Then so it just increased the pointer. So and then you can just understand that the pointer is the address of a variable, right? So In this example, so we just declare the pointer type variable, right? P, right? So if we use this symbol, then it represents that this data type is the pointer type. And then you can find that the pointer, this pointer, the start point of this pointer P is the base address of array, right? So this is the array 0, and then it should be less than the 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 last element, the last element of array, right? And then the pointer is just increased. So even though we use the p equal p plus 1, but this pointer is this pointer type is the integer pointer, right? So if we just increase the p by 1, it means that the address is increased by the size of integer, right? And then what does that mean? It means that the data of the memory space pointed by this pointer value, right? So it is clear. So actually, this is the equivalent code. So left side code and then right side codes are equivalent, right? But we can use the array in this code, and then we can also implement the same code using pointer. Okay. So if we directly translate these two codes, like array version and then pointer version, then we can write the assembly RISC-V assembly code like this. So this is the array version. This is the pointer version. Actually, these functions are equivalent, right? But what is different? The difference is that, so in the array version, inside of the loop, we can observe how many instructions? 5 instructions. Okay. And then in the pointer version, we can observe that inside of a loop, we can find 3 instructions. So you can find the move instruction here. And then I mentioned that move is just a pseudo instruction, right? So even though the functionality is the same, but the translated assembly code can be different, right? This is the array version, and the left side is the array version, and then right side code is the pointer version. So which version is better? So what does that mean? I mentioned better. So which means which one exhibits higher performance. So which code is better? So which means that, so which code exhibits the higher performance? Which one is better? The left or right? Left? Right? Okay. Yeah, right code is better. Why? So it is because, so you can use the equation, the how the performance is defined. So T, the execution time, T execution is the instruction count and CPI, and then TC. Okay. So TC is the hardware part. We cannot change this one in using the software. And then if the CPI is the same for all instruction, then instruction count decides the performance, right? So if the instruction count is if there are more instructions, then the performance is decreased because the execution time is increased, right? So why? This left side code includes the 5 instructions in a loop. So if this loop will be repeated the size times. So it's a So if the size of an array is 100, then this loop will be repeated 100 times. So how many instructions? This when this code is executed, then 1 plus 5 multiplied by n instruction will be executed, right? Because there are 5 instructions in a loop, right? And then n is the number of repetition, number of iteration of this loop. How about, but this code has the 3 initialized code, okay? So it's a 3 and the number of instructions is the 3 plus 3 multiplied by n. So n is the iteration number. So if the n is large, then you know the 5n is larger than 3n, right? So that's why this right side code is the barrel code. Okay. Then you can work. You can think that in order to write a barrel code, then we can use the pointer, right? Is this the lesson from this slide? So yeah, actually you don't need to worry about the code optimization. So we can use the array version, okay? So this is because even though we use arrays, and if even though we access array element using array indexes, and then these operations can be optimized by compiler. Okay, so even though we write a code like this, but compiler can generate the code assembly code like this. So you don't need to worry about the array version or pointer version. Okay, so actually compiler can achieve the the optimized code. Compilers can generate the optimized code from the array version. Okay, so actually we can write the code clearer and safer. So what is the problem of a pointer? So pointer means that, so if we use pointers, then we may access the some incorrect data, because we can store any memory address in the pointer type data, right? It means that we can access the some incorrect data. So, and then this can be the source of bugs. Okay. So the recently the United States government prohibit the use of C, right? Because so they think that C is not safe, because using a C, so so C has the pointer type data, right? And then using this pointer type data, then we can just change the address of a variable. So which means that we can access. We may, but some data is probably prohibited by operating system, but sometimes we can access some different location of memory using C. So that's why the US government does not like C, because it's not safe. It's not secure. Okay. Okay. So now so let's learn about the machine language. So until this point, we learned about the basic RISC-V instructions, right? But when I mentioned about the RISC-V instructions, so we learned like this. So this is the add instruction. This is the sub instruction, like add x1, x2, x3. So actually, so we can understand instructions using the alphabet, right? So these are characters A, D, D, right? It's not numbers. Those are not numbers, okay? But we learned that CPU or processors can only understand the digital data, right? What are digital data? Like binary numbers, 01, 01, 01. So what does that mean? So actually, so CPUs cannot understand the assembly instruction, obviously, right? So these instructions are represented using human, not human, it's not language, it's a human letters, okay? Like English letters, right? So it means assembly instructions. RISC-V assembly instructions need to be translated into the machine language, like the binary language, okay, binary data. Then understand, processor can understand the instructions. So, let me see. Where is the? How can we change the? So I don't. Where is the tab? Okay. So, so in the dump file, so actually you can, so this is the lab document, right? So in the dump file, you can find this code. So, and then because we learned about the RISC-V instructions, so we can understand, oh, these are RISC-V instructions, right? And then I mentioned that these numbers are program counter, right? It's a PC. So it means that 10074 is the PC of this RISC-V instruction, right? And then you can find the hexadecimal number here. Actually, this number represents the machine language, the machine code of this instruction. Okay, so you can find that this is the FD010113. This is the hexadecimal number. So because if we use the binary number, then this number can be very long, right? So it's a 32-bit numbers, right? So actually this is the 1111. What is T? 1001? No, no, what? 11. I don't know. I don't know. So it can be represented using binary number, right? So actually, this is the real binary data. It's the real instruction for CPU or RISC-V CPU, right? So this is C. Actually, this is 1101. So actually, this RISC-V instructions, RISC-V assembly instructions need to be translated into the machine code. And then in this time, so we will learn how assembly instructions are translated. It is called the encoding, right? How the RISC-V instructions are encoded into the machine code. Okay. So as I mentioned, computers can only understand the 1 and 0 is a binary data. So it means that the instructions need to be represented using binary data. And then in the RISC type instructions, actually every instruction occupies the same size of the binary data field. So in a RISC-V, a single instruction is represented using 32-bit binary data, right? 32-bit is the 4-byte, right? It's a 4-byte. That's why the PC is incremented by 4, okay? So, like the add I instruction, add I, SP, SP minus 48. So this can be translated into the 42-bit machine code like this. So this is the example. Okay, add S. So this is add I actually, but you can use the add in the this is kind of pseudo instruction. So this can be represented to this is represented to this binary data. Then for this encoding, so this is called the encoding, right? So this is the binary translation. Then we also need to use some rules. Okay, so RISC-V defines the 4 different types for this instruction representation, the instruction encoding. So these instructions, in the RISC-V instructions can be categorized into R type, I type, and then SP type, and then UJ type. Okay, let's see the example. So R type means that is the register type. So R represents the register. And then the example of this R type instruction is the add instruction. Add X1, X2, X3. Right. In this add instruction, the add instruction requires 2 source registers and 1 destination register, right? So, and then other instructions such as the OR, and also sub. Some other instructions also have the similar forms, the R-type form. So these instructions have 2 source registers and 1 destination register, right? So then we need to represent this instruction into the 32-bit machine code. So this is the rule. So this is the encoding rule of the R-type instruction. So in this rule, you can find that the LSB, the pin number 6 down to 0, is the OP code field. So this is the OP code. And the next 5 bit is the RD. RD represents the R is the register, and then D represents the destination. Okay, and then the next 3 bit is the function tree. Okay, function tree field, and then you can find this is the RS1, this is the S represent the source, so it means that source register 1, and then RS2 is the source register 2, and then the next 7 bit is the function tree field. So this is the encoding rule. Sorry. The encoding rule of the R-type instruction. What does that mean? So why RD occupies the 5 bit? Why? So what is this code? Why function 3 and function 7? So think about this. So this is the add instruction, right? So which information is required in order to understand that, oh, this instruction is the add X1, X2, X3. Firstly, a CPU needs to know, oh, this instruction is the add instruction, right? And which information is required? we need to know this number. So this is the destination register number. And then also we require, the CPU requires source register numbers, like this is the RS1, this is the RS2, this is the RD. So which information is required? We need to know. So CPUs need to know, oh, this is the add instruction. Oh, then this destination register is X1. And then two source registers are X2 and X3. So these are required information, right? So this information needs to be included in the machine code. And then this is the encoding rule. So as you can see, this R-type instruction includes the RD field, the 5-bit, RS1 field. So which means that this number is stored in this RD field. And then this is the RS1. This is the source register one number of source register. So this register number is stored in RS1 field, and then source register number 2 is stored in RS2 field. And other fields such as the OP code, function 3, and then function 7 fields are used for representing add instruction. Okay, using these 3 fields, we can represent the add instruction. So then why RD requires 5-bit? So it is because, so we learned that the number of general purpose register in RISC-V is 32, right? So this number can be number 0 to 31. That's why the RD field requires 5-bit. So the smallest number of this register number is 0, right? And then the maximum number is 31. So in order to represent this range of numbers from 0 to 31, we require 5-bit, right? So that's why the RD field occupies the 5-bit. RS1 and RS2 also require 5-bit fields, right? And then, as I mentioned, other fields are used for representing, identifying, add instruction. So this is the example. So this is the assembly code add S2, S3, S4. So in this example, we just use the ABI name for the registers, right? So this is the S2, S3, S4. And then also in the dump file, so you can find that in the dump file also you can find it uses ABI name of the register. But actually, in a CPU, this ABI names of the register needs to be translated into the register numbers. Okay, so actually the equivalent code, so equivalent instruction of this add S2, S3, S4 is the add X18, X19, X20. So what does that mean? This is the RD, this is the RS1, this is RS2. So it means RD, the destination register number is 18, this is 19, this is 20. So we can just fill 18, 19, 20 in the RD fields, RS1 field, and RS2 field. And in order to represent add, we can use the function 7, function 3, and OP code. And then this is defined by ISA, instruction set architecture document. So for the add instruction, the OP code is 51, and then function 3 is 0 and 0. So we can fill some numbers in each field, and then if this needs to be represented using binary number, right? So we can just translate this decimal number into binary numbers, right? So 51, 011, 0011, 18, 10010, something like this. Then it becomes this machine code, this data becomes the instruction of this add S2, S3, S4. Okay, so I believe you can understand how the instruction is translated into the machine code. Then it can be using the hexadecimal code. It is this number, this hexadecimal number. The another example is sub T0, T1, T2, and then it's actually sub X5, X6, X7. So we can fill the RD, RS1, RS2 like this, and then in order to represent sub, OP code is 51, and function 30, function 7 is 32. So we can just translate the decimal number into binary numbers. Then we can make the machine code. So this is the example. Okay. And then this is the R-type example. So which means R-type instructions. R-type instructions have the same encoding rule. Okay, like this. Okay. So and then the another type is the I-type instructions. So in the I-type, I represent the immediate type. So it means that I-type instructions include immediate number. Okay, so what is the immediate number? Immediate number is the 12 bit 2's complement number, right? So for example, add I is the example of immediate type instruction. So add I, RD, RS1, and immediate. So for example, add I, X1, X2, and -1. So which information is required to represent this instruction? So like the R-type instruction, we need to know the destination register number, and then RS1, the source register number. And then another data is the immediate number, right? And then we need to represent add I, right? So this information is required for representing this instruction. So this is the encoding rule of the I-type instruction. So you can find that the first 7 bit is the OP code field, the same, right? And then next 5 bit is RD, and then function 3, and then RS1. So what is different? So actually in the I-type instruction, RS2 is not required, right? So other fields, the remaining fields is used for immediate data. And you can find that this immediate data is the 12-bit data. So that's why I-type instruction like add I can only use the 12-bit 2's complement binary number, right? Do you understand? It's just because this instruction needs to be translated into the 32-bit machine code. But in order to include this immediate number, we just have only 12-bit field, right? Right? So this is the I-type instruction, okay? Okay, let's see the example. Example is add I. So add I, S0, S2, and then 12. So this needs to be translated into the register number type. So add I, X8, X9, and 12. So this is the destination register. So we fill 8 in the RD field, 9, so RS1, and then 12. 12 is the 12, immediate number. And then in order to identify add I, so we need to use the function 3 and then OP code field. The OP code field of this add I is the 19, and then function 3 is 0. And then this can be translated into the binary number like this. So this becomes the 32-bit machine code, the 32-bit machine instruction of this add I. Then CPU can read this 32-bit data, and then it can figure out, oh, this is the add instruction, add I instruction, right? By checking OP code and then function 3. And then RD is the 10000 is 8. RS1 is the, oh, this is the 9. Oh, immediate is the 19. So by decoding, so this is by checking each field of a machine code instruction, then CPU can figure out the assembly instruction. So this is another example add I, so but immediate is minus 14. So it's a minus 14, and then so this becomes the 11111110. Okay, so this is the 12-bit 2's complement number. Also, another example of I-type instruction is the load word. Right. So load word requires the destination register and source register. This is RS1 and offset. Offset is the 12-bit immediate data. So load word is load instruction. Load instruction is also the I-type instruction because the load use includes the immediate data. So this is the destination. Oh, RS1 is the 19, and then immediate number offset is the minus 6. Okay, we can just fill each field using the numbers. Okay, numbers in this instruction, assembly instruction. And then load instruction, OP code, and then function 3 is different, right? So in order to identify load, so we can use the different OP code and then function 3 field. Okay. So this is the I-type instruction. Okay. And then S-type and B-type. So S represent the store, and then B represent the branch. So when you use the store instruction, actually store instruction is used, then actually store instruction includes the 2 source registers, right? Like the RS2 and RS1 and offset. Okay, so this is the example of store instruction. So if you see the store instruction, you can find that store instruction requires the RS2, the source register, because store instruction reads data from register, and this read data is stored in the memory. But in order to access the memory, we need to calculate the address, right? So this is used for calculating the target address, and then this RS2 is used for accessing register file. So store instruction requires 2 source registers. Then how about the branch instruction? So if you see the branch instruction like a BQ, RS1, RS2 and target. Target is the immediate number. Okay. So if you see the branch instruction also requires two source registers like RS1 and RS2 and target. In order to represent the target, we need to use the immediate number. So as type instruction, the store type instruction can be represented like this. So in the store type instruction like SW, these store instructions do not include RD. Okay, so there is no RD here. RD is not here. So RD is not used, but it uses RS1 and RS2, right? And then we can use the remaining bits for the immediate data. So you can find that immediate data also occupies 12 bit, but the the bit number 11 to 5 occupies this part, and then bit number 4 to 0 occupies this field. So it's a little bit different, right? It's an I-type data. The immediate field just occupies the pin number 31 to 20, right? But in the S-type data, the immediate field is just separated. And then so upper part is stored in the pin number 31 to 55. And then the lower part is stored in the pin number 4 to 0, the pin number 11 to 7. But P-type, it's a little bit different. So only the immediate field is different. So if you just see the P-type instruction, you can find that in the lower part just stores the immediate number 4 down to 1 and in number 11. And then in the B-type, the immediate number 12 and then 10 down to 5 is stored in the upper part of this instruction. So that's why, so I mentioned that when we use the target, so I mentioned that the label needs to be translated into the target of a branch instruction. But in order to, this target needs to be translated into the number, right? But this number needs to be multiple of 2, the even number, right? This is the reason. So you can find that immediate 0 is not here in the B-type instruction. So if the LSB, the bit number 0 is 1, then it's the odd number, right? But you can find that immediate 0 is not here. So instead, we can just store until the bit number 12. So immediate 12, right? So that's why when we use the branch instruction or jump instructions, we need to use the even number only. Okay, odd numbers cannot be represented. Odd numbers cannot be translated into the machine instruction because of this encoding rule. Okay, so it's a little bit, so S type and B type instructions include only two source registers and immediate data, but the encoding rule is a little bit different. Right? So in order to encode the immediate number, the bit type is a little bit different. Okay. Okay. So this is the Pseudo instruction. Okay. And then this is an example of S-type example. So like the store T2, S3, and -6, right? So we can use the register number. So this is the RS2, this is the RS1, right? So we can just fill the field. field, RS1 field, RS2 field is the register number, and then offset is -6. So using the we need to fill the 111111 and then 11010, right? 11010. How many ones? One. Okay. So this is the immediate number, right? So this lower 5-bit needs to fill this immediate field both down to 0, and then upper 5 to 6, 7-bit needs to fill the upper 7-bit part of this machine code field, right? So it can be translated into binary code, and then this is the machine instruction, right? P-type. So P-type also has the 2 source registers, but immediate is a little bit different. It has the immediate 12 to 1. Okay, you need to remember this. Okay, so a little bit different. Okay, so then immediately can be field this immediate field like this. Okay, so this is some example. Okay, so in this example, so you can use the BQ here, and then the label of BQ. The target of BQ is L1. So where is the L1? L1 is here. Then what is this number? This number is, so this is target. The target 0x80 minus 0, the piece of the BQ, the 0x70. So what is this number? 0x10, right? It's 16 in decimal number, right? So we can write this assembly code using the decimal number like PEQ, S0, T5, and 16. Okay, so 16 is the immediate number of the BEQ, right? So this is the 16, right? 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, right? This is the 16. You know, this is the 1, 0x, 1, 0. So this is the 1, and then other numbers are all zeros. And then this is the pin number. So pin number is 12 to 0. And then actually in the RISC-V machine instruction, only this part is included in the machine instruction. So the branch is a little bit tricky because of this issue, right? So immediate can be included in the machine instruction in the weird way, right? So this last bit is removed. It's just thrown away, and then we just include the pin number 12 to 1. Okay, and then using this encoding rule. Okay, so other part is the same. So RS1 is 8, RS2 is 30, and then the OP code will be, we can just use the OP code of BQ and then function 3 field, right? And then in order to fill the immediate number, the 12-bit is 0. So 12-bit is 0 here. And then what is the 10 down to 5? 10 down to 5 is this one. Then this one is stored in this field, right? And then this the row part. The row part starts from the 4 down to 0, right? So what is the 4 down to 0? It's 1, 0, 0, 0, right? So this is included. And then what's the last part? Last part is pin number 11 here. So immediate number of the branch instruction can be encoded into this machine instruction like this. So you may think this is it's a little bit weird, right? But actually, if we just consider some hardware implementation, then you can think that we can share we can share some hardware resources. So actually, this encoding rule is designed for hardware implementation, the simpler hardware implementation. Okay. So okay. So this part is a little bit tricky, but it's just the rule. It's just rule. Okay. So so you can uh just understand understand this rule. Okay. So this encoding rule. Okay, so I will stop here and then I will explain the other types later in the next class. Any questions? Okay, thank you for your attention. See you in the next class. 감사합니다.